Good afternoon. I hope you are able to hear my voice. At least one
Yes,
yes.
yes, sir. Yes, sir. Can hear.
Yes,
Okay,
sir.
fine. Thank you. Sorry for the delay. I'll share the screen right now. Yeah, my goodness. I hope others are also able to join without much difficulty. We'll proceed. Last class we discussed about the electromagnetic radiation and its applications to a great extent. How they can find the way starting from the universe till to the humans, where they can have the creativity in utilizing the energy or electromagnetic radiation or electromagnetic energy in employing for its applications. Actually, we will continue with some of the techniques. Actually, last class of course last two classes maybe we generally discussed about the topics on electromagnetic energy, which is an introductory part, and the electromagnetic energy, that is the continuation. We will deal with the blue color, whatever it is highlighted on second topic. There is a loss regarding the amount of energy which are radiated from an object, where you will encounter with either 3 or 4 laws, doesn't matter actually, 3 or 4, how that these laws can be used or how that they have arrived. Means there is the scientists, either Planck or Wien or Legend or Stephen. It is one of the law is missing here in this part actually. How they have arrived for the how they have arrived for this kind of a laws, but for making use of the electromagnetic energy, that will think it off actually. While sending the link, maybe yesterday or day before yesterday, I told that we are surrounded by radiation. We are surrounded by electromagnetic radiation of all the wavelengths to a great extent. Actually, how that can be utilized, how that can be employed. Actually, let us see one after the other. It is not a big issue to deal with those type of the things. Where you are having familiarity with these 3 laws, starting from your high school days and till you might have very experience in handling these type of the topics, either in modern physics or maybe the electromagnetic radiation to a great extent actually. Okay. Planck is the one who has made the physics relatively difficult compared to the Wiens and the Rayleigh, that we'll see later. From the beginning, I'm showing one slide for you actually about the electromagnetic radiation. It is not one single kind actually. This is the broad spectrum, what you observed earlier too, to a great extent. In order to the panel, I'm keeping it as the background. Don't worry, we'll go with the statements how it can be defined actually. In order to best make use of the information that comes to us, particularly via the electromagnetic spectrum, what it has shown, starting from 10 to the power of 6 hertz to about 10 to the power of 21 hertz, it is now almost an order of magnitude of about 15 to 16 order of magnitude, with a difference in the wavelength few meters to a few angstroms to a great extent, or maybe energy also spreads out from very small electron volt to of the order of giga electron volt, even sometimes peta and tera electron volts of that kind. The energy which comes to us actually, or we can make use of the information what we are having actually, that comes to us via some kind of a media, they can call through a spectrum called electromagnetic spectrum, or maybe in terms of an electromagnetic energy. We need to understand some of the basic properties of the radiations. There is no doubt in it actually. You are well aware. We will again recapitulate our understandings in how that electromagnetic radiation or electromagnetic energy is employed in understanding the phenomena which are happening in and around us actually. A complete treatment on the subject of this radiation theory, they can call, okay, would take an entire course. Need not be a PhD coursework of 1 or 2 units, or maybe a few portion of the unit actually in a unit, because it is a big in a sense related to a larger content actually. If you go deeper into the subject, certainly it is having its own coursework of that kind. Doesn't matter. But how we can be employed, that we'll see later. We will see here actually. Instead of that, for example, if you just want or if you just need to know the fundamental principles which are describing the electromagnetic radiation, how that electromagnetic radiation originates from an object, or how that radiation travels through the space, if you want to see, there are fundamental laws. There are fundamental laws. You can't call them as a rule, you can call them as a law itself. For an electromagnetic radiation, there are 4 laws that describes the type of amount of energy being emitted by an object. Means that depends on the type of the energy which is emitted by an object. Depending on that, we are having the 4 laws. Now, being a research scholar at the PhD for the PhD program, maybe initially means almost 1 year is over. You are in the second year right now. You are enjoying a lot actually. Why four laws? Because you might have seen the gravitation law, universal gravitation law, only one single law. Okay, maybe our Newton's laws. Maybe that maybe differ for inertia, differ for momentum, differ for the force. Different laws. Maybe Kelvin's law, or maybe what we can call Kirchhoff's law, or maybe you can call it as in voltage law, current law, or Fleming's left-hand rule, or Fleming's right-hand rule, or something like that. They are unique laws in a sense. But for the electromagnetic radiation is considered, only single law is not sufficient actually. It has to go with the four laws in the sense. Means one law is not sufficient, or one rule or one concept is not sufficient to explain, or one law is not sufficient to describe the phenomena that are happening for the entire electromagnetic radiation to a great extent. Means it has to cover the left extreme of the very long wavelength to a right extreme of the very short wavelength with high energies that are capable of having the entire magnetic spectrum, electromagnetic spectrum in different ranges, different wavelengths they can call actually. We can say that with the radio waves, then microwaves, infrared, ultraviolet, X-rays, and gamma rays. Still, it is good enough. If you it is good enough if you are capable of understanding the phenomena, with an Indian. Hello, Nagaraj, are you not able to hear? Okay. Still, if you are unable, still if these four laws are capable of giving us the description, giving us the information what we want actually from an object, that it's good enough actually. We'll see how it has to go. No need. This spectrum you have seen in previous classes in earlier also actually. The visible range I am enlarged actually to a great extent where it covers from violet wave diode they can call, starting from violet on the right extreme to the red on the left. If you keep the prism, in terms of the energy, it should be an increasing energy as you move from left to right. In terms of the wavelength, it is decreasing. In terms of the frequency, also it is decreasing actually to a great extent. In science, for example, here a law is used to describe a body's observation. Means a law, any kind of a law we can call, particularly the thermodynamic laws we can expect actually is used to describe a body of observation. Means when the law was established long back, maybe a few centuries back actually, no exceptions were found. Okay, that contradicted the statement that the law is used to describe a body's observation. Something is white, something is black, something is red, something is brownish, or something is darker, something is brighter, something is relatively of different, maybe you can call it as an intensity, relatively you can call it as in different contextual places as a context actually, that can be established, that can be observed. Through the observation only one can do that. Those observations were dealt with in the certain laws. There is no contradiction out of it actually. But the difference between a law and a theory is that a law simply describes something while a theory tries to explain why something has to occur. Remember, being a scholar at the PhD program, particularly great subjects like in physics, you should understand the difference between the law and also the theory. Law try to explain simply how that things are going on, something which is how the things are going on. But the theory that explains in detail, or the theory tries to explain why that something is happening. For example, if you allow a stone, if you allow any massive body from a certain height, it has to fall down. Okay, Newton's laws tells us that it has to fall towards the heavier mass. Fine, that's good, towards the earth. For example, if you're dropping a stone, or maybe if you're dropping a moon, for example, I'm guessing actually, if you drop a moon from a distance of about 4 lakh kilometers, now it is with the influence of the gravitational influence of the earth, it is attracting towards the earth. Assume that if Venus comes nearer to the moon, or assume that if Saturn comes nearer to the moon, assume that if a Jupiter comes nearer to the moon, for example, rather than the distance what we expect between the distance of separation between the earth and moon may be under the larger gravitational influence or higher gravitational influence of an heavier mass rather than the earth. If you allow that, with reference to an observer on earth, if an heavier mass is approaching the earth-moon system to a great extent, moon may be pulled away. Maybe if I have an observer over the Jupiter, for example, it gets attracted. Then the statement what I want to say here is that always the objects will not fall down. Objects will not fall down. It may fly also. Fly in the sense, for an observer who is in an opposite frame of the reference that appears to be moving away from the observer, it may not be fly in general, for example. Okay. For example, if you take in all the elements which are in the air, which are in the atmosphere or in the space to a great extent, are bounded together with the earth to a great extent, including the heavier molecules like nitrogen, oxygen, argon, neon, carbon dioxide, monoxide, sulfur dioxide, all of them are in the gaseous form. You thought that at least what happened to the fate of an hydrogen? What happened to the fate of an helium? What happened to the fate of an neon? What happened to the fate of an argon? Of course, still about 1% exist for the Earth, for the planet Earth actually. What happened to them? They are the later elements in a periodic table. Of course, they are also the later elements in terms of the atomic mass unit. The gravitational influence which is acting on or acted upon by acting on an hydrogen atom or hydrogen molecule is relatively quite less or feeble compared to that which is acted upon an helium or neon or lithium or argon of that kind by the earth, by the huge celestial body earth. What happened to the fate? Maybe last 100 years back, last 100 million years back, maybe the possibility that earth might be composed of more hydrogen that might have escaped from the gravitational frames. The contribution or the contribution in terms of the percentage of the contribution we can call, what it was right now might have reduced, particularly for the later elements, because those elements were not bound relative to that of the nitrogen or oxygen or argon compared to that. Means to say that, means the same law, is it valid right now? The Newton's law, what it was saying that a body which has to fall down, actually, it is explaining something phenomena. But theory tries to explain why that something has to occur. Why that has to occur? Means you might have that the product of those two masses and inversely proportional to the square of the distance between them makes thus that how much force is acting on a lighter massive body with reference to the heavier mass, or quite vice versa too, to a great extent. Moon is also attracted towards the earth, there is no doubt. At the same time, earth is also attracted by moon. Both are in a what we can call acting in a perfect way. They are kept it in a solar system with a distance of about 150 million kilometers as the celestial forces are considered. Okay, as you read these through the laws, for example, think about observations from everyday life that you have made so far might support the existence of each law. Either Jeans law or Wien's law, Rayleigh's law or Planck's law that has to support. Means to say that actually these laws have to support our daily observations, or whatever we are observing, we should have the answer. We should have the conceptual answer for the phenomena which are happening in and around actually. Okay, people sometimes we may visualize, most of the time we may not visualize. What is a great thing actually, falling an apple actually from a tree, it is not a big issue. Newton at that time has a thought why it has fallen down. Then the law came into an existence such a way that he developed a theory to give the description for the falling of an apple towards an earth actually by some phenomena is known as something attracting phenomena is known as the gravitational phenomena. Means something it is against to that, certainly can have another law or maybe anti-Newton law they can call actually, that you try, because everything happens in science, everything happens in research, that also a term bomb. Okay, but certain laws like in gravitational law, they are the universal laws, need not restriction for the era and need not restriction for the space, need not restriction for the zone. Okay, it is valid everywhere, every time, all the time, and all the mode of that kind. Being this, let us see 4 laws. I'm not going much actually in the sense. Within the time frame, you try to understand what you learned so far earlier actually. Planck's law, what it says that every object emits the radiation at all times and also at all values. Good. There is no doubt in it actually, because we know whichever way the object which is possessing certain radiation, it must be emitted. Every object emits the radiation at all the time, is no restriction for the either morning or evening or night time, no restriction for either summer or winter or the seasons of that kind. And it also emits in all the wavelengths, all possible wavelengths, we can say that, for example. If you think about it in detail, for example, the same Planck's law, E is equal to H times nu, or E is equal to H times C by lambda, HC over lambda they can call. Okay, either in terms of the wavelength or in terms of the frequency, or maybe depending on the frequency, or maybe depending on the wavelength, you are having energy. Or quite reverse, depending on its energy, the object has to emit the radiation either in particular wavelength, or maybe a particular frequency, or maybe in the range of the frequencies, or maybe in the range of the wavelengths to a great extent. What do you think actually here? If we think about it in great, okay, this law is pretty hard to wrap your brain around it. In the sense, you can't protect your brain from the radiation which are falling every minute and all the time, every minute from all the directions. Okay, we know that the sun emits the visible light. See the spectrum on the left bottom extreme actually. Infrared waves, I have not shown here actually. Radio waves and X-rays. Okay, sun emits the radiation. Okay, in which domain it emits radiation? Either radio waves or X-rays or gamma rays or ultraviolet radiation, or maybe thermal radiations, or maybe visible radiation from red color, or maybe blue color, green color, or violet color, pink color. That one has to say that. Means to say that it emits radiation. There is no doubt. Okay, these are the two spectrums which were observed, they can say that actually there is no doubt in a particular frequency domain or particular wavelength domain in such a way that left one is the sun's emission in the visible range between 4,000 to about 8,000 angstrom what we expected. This is slightly lesser than that wavelength or maybe higher energy of that kind in an ultraviolet emission of the sun. Both are appearing the same thing. There is a circular disk, there is no doubt it. But some phenomena you can see on the left extreme, the left side in such a way that there are some spots, there are some dots they can call. They may be under movement or not moving, actually they are static. That we will see later. Those spots are known as they are known as the sunspots. Relatively they are black in color, what they expect. Relatively they are darker. Now, you may be thinking that if you get a spectrum of this kind, or if you get a photography of this kind, photography need not be in the visible spectra, let it be in any kind of a spectra of that kind. If you take a photography, can you identify a dark spot if the sun is at a temperature of about 6,000 degree Kelvin? Because so far you accepted all the concepts, whatever it was told, either in my classes, previous two classes, or the physics teacher who has taught from almost high school, maybe like science teacher at that time, or maybe in +2, or maybe in graduation or master degree. Means sunspots, some of you, those who are from Bangalore University, have done some experiments, particularly in estimating the time period or periodicity of the sidereal day, or length of the sidereal day and the length of the synaptic day of that kind, where you have given some disk with some black spots, where you estimated that moment of those spots actually as a time frame, how long they will take to move from assume that point A to point B, or from left extreme to right extreme. Okay, then you might have estimated. Is it possible to take a photography of any object which is in between sun and us, particularly if the spots are occurring on the sun? Can you expect that some kind of a black spots are occurring? Because the temperature is of the order of about 6,000 degree Kelvin. What kind of a black spots you can put? They are known as the regions, maybe of the order of several hundred kilometers, okay, thousands kilometers of that dimension, okay, of the area where the temperature of those regions are relatively less by about 2,000 to 3,000 degree, usually 2,000 to 2,500 degree Kelvin, lesser than that to its environment. That is why relatively they are appearing black, relatively they are appearing dark compared to its environment. Those are the regions with the change in the magnetic field, and that change in magnetic field leads to the movement of the spots they can call. That is known as the sunspot. There is a periodicity, there is a periodic nature, there is a signature, there is a kind of a signature by the sun to emit the radiation in particular domain. Actually, by studying those type of the phenomena or the periodicity, one can able to say that whether the sun is active or quiet or mild. Okay, it will never be a quiet sun actually. It will never be done. You can't switch off the radiation from the sun actually. It is a huge nuclear reactor that emits the radiation continuously without breakup of the radiation, starting from ever since it was started almost 4.55 billion years, and it will continue emit the radiation for another 5.5 to 5.6 billion years. Thing is that here we are still in the second statement in such a way. Sun emits the radiation in the visible region, no doubt that we found it out. Sun also emits the radiation, also means sun emits the radiation. That's all. What kind of radiation? The left spectrum is observed in visible, the right spectrum is observed in the ultraviolet. Okay, means the sensors used to detect the radiation are the sensitivity to the ultraviolet radiation, or the interaction of the radiation with the sensor is in UV band or in ultraviolet band or ultraviolet domain of that kind. Here you are seeing some spectacular phenomena of some curly nature of that kind, like an faculae or maybe such type of the things that I will not go in detail actually. See that in terms of the electromagnetic radiation, the Planck's law is used, the Planck's law has employed to understand the objects, behavior of an objects, or making some kind of an observations continuously. One can evolve in what it is made up of, how it is made up of, what is its dynamics going on of that kind. Okay, it emits, means that is the sun emits radiation in microwave, radio waves, and also X-rays. Oh, can we see the X-rays if it is emitted? Actually, sun is a big nuclear furnace. Of course, people who are working in material science are working a lot on furnace. Maybe the temperature they may change for some certain samples to see the behavior of the temperature, to see their criticality, maybe a few hundred degrees Celsius to about few thousand degrees Celsius. Sometimes they may go about 1,500, 2,000 degrees Celsius also. Such type of facilities are available in our own department, no doubt. And sun is also one big nuclear furnace. Sun acts like one big nuclear furnace. If you want to have the studies of your sample, how that sample changes its properties, either electrical or thermal or maybe magnetic or maybe some kind of a properties actually. Okay, try to take those samples to the sun. It is a big oven actually, big oven, big furnace they can call, and it emits all sorts of the electromagnetic radiation, starting from radio waves to and gamma rays to a great extent. However, what Planck's law says? Planck's law says that every object emits over the entire electromagnetic spectrum. Need not be sun alone, where it is maintained at 6,000 degree Kelvin. Whatever you are seeing, that means to say that whatever the radiation that is emitted by an object which is surrounding us. For example, maybe right now you are listening to my class. You may be having surrounding some materials like maybe a table or maybe wall or maybe some clocks or pen, your mobile. Every element, every object they can call actually. Every object emits the radiation which is surrounding us. Is it true? If it is true, what kind of a radiation it has to emit? That we'll see. See the right bottom text actually. These colors, what we are expecting from the sun. Sun looks white during noon hours, looks like reddish color during either sunrise timings or maybe sunset timings. Moon also the same case, appears to be white, but the astronomers, particularly the media bureaucrats, have mentioned that blue moon, red moon, black, not black actually, and reddish moon of that kind. Is it such type of colors are happening really, or is it something with other phenomena which are making them in a different color, where we could not able to explain those theories based on our imagination? What it says is that colors in these images, particularly these two images, either white, relatively white they can call, and the blue color you can expect, are deceptive. Deceptive in the sense it is an imagination color. There is no sense of color in spectral regions other than visible light. But the use of these colors are known as the false colors to make our imagination, where the images can be read by our own eye, depending on the intensity of the radiation, particularly of one wavelength. Wavelength maybe belongs to the ultraviolet category, or maybe physical category, or maybe something else. These two images are brought from the NASA, in the sense. Thanks to the NASA for maintaining such type of an imagination. Now, question lies. What question lies? If we say the previous statement, you emit radiation at all wavelengths, I too emit radiation at all wavelengths, you too emit radiation at all wavelengths, instead of calling names by some XYZ or depending on your name, can we identify a different persons depending on the emission of their wavelengths? For example, somebody emits about some X, lambda X, somebody emits lambda Y, somebody emits lambda Z, somebody emits lambda A. Maybe only in 26 alpha numerics are there, alpha 26 characters are there actually in English, but may not be sufficient actually. Now, question lies is that whether we are emitting the X-rays in any measurable amount or not. No. Thanks. If not, if we are also emitting an X-rays, the life was tough task actually, such an high radiation. What happened? The Max Planck, actually a great mathematician at that time, hinged on the fact or gave the fact, gave worked on the fact in such a way there is a wide distribution of vibration of speeds for the molecules in substance. Molecules are not static, molecules are vibrating with a huge speed. That movement of those molecules at a greater speed leads to the emission of the radiation in a particular wavelength. You can say that jumping of an electron from higher energy level to lower energy, these are relative terminologies, which is higher, which is lower, that you have to decide actually, that varies from element to element, that varies from composition to composition. This means that it is possible for matter to emit radiation at any wavelength, but in fact, it does to a great extent. But another misconception what we are getting from this law is that it dispels, it disapproves in such a way that the matter selectively emits the radiation. Assume that, for example, iron emits in particular wavelength, gold emits in a particular wavelength. Is it true that you just think it off? Those who are having already started with the analysis of the spectrum, either in XRD or maybe in Raman or maybe in FTIR, that you can think it off. Or even though you might not have took the samples for the analysis, you might have come across in the literature in such a way that each and every individual will emit the radiation in particular wavelength of that kind. Let us see how it happens. What happens when we turn off light bulb? What happens actually when we turn off light bulb? Of course, during daytime you are having insufficient light, you may not distinguish. Okay, during nighttime, if that is the case, if you turn off the light or switch off the electric lamp, okay, off of a light bulb, the light bulb switches off. Is it still emitting the radiation? Yes. You might be tempted to say no, because the light is off in dark. But what about the Planck? He never thought like that. He told in the previous slide in such a way, what we discussed, while the light bulb may no longer be emitting radiation that we can see in the visible, but it is still emitting at all wavelengths. Most likely, it is emitting the huge amount of radiation, particularly in infrared. Means to say that any object, if it is at any distance, any temperature, they have to emit. Can you expect an object at a 10 degrees Celsius will emit? Yes. Can you expect at 200 degrees Celsius? Yes. At 1000 degree? Yes. Any temperature beyond that? Fine. Can you expect that minus 10 degrees Celsius, an object emits the radiation? Or minus 10 degree? At least I need from chat box, if you say yes or no. Can you expect the radiation is emitted by an object which is maintained at minus 10 degrees Celsius, or maybe minus 20 degrees Celsius, minus 100 degrees Celsius? Yes or no? If you yes or no, if you are no. All objects above 0 degree Kelvin emit the radiation. In the sense, even if they are maintained at about minus 273 degrees Celsius, they have to emit. All objects which are maintained above 0 degree Kelvin, they can say, absolute temperature, they have to emit the radiation. Need not be negative temperature of that kind actually. Ice is maintained at about 100 degree water, 0 degree, you are saying that. It may go even for sub-zeros also. Still it emits the radiation. But thing is that the emission of radiation may not be in the visible region of that kind or visible domain of that kind. See, let us take another example here actually. If you hear an occasionally, of course, where our CS Patil sir is there actually. Yeah, he is there actually right now. In a TV, he is also one of the, not one actually, one among the great personalities. They are giving the prediction. What the predictions they will give? If you hear the occasionally on TVs, on weathercasts, when the sun sets, the ground begins to emit the infrared radiation. When the sun sets, means after sunset till sunrise, they expect that the sun emits the infrared radiation. Means to say that don't think that the Earth emits the radiation, Earth emits the infrared radiation during daytime. It goes in such a way, the Earth emits the radiation during nighttime infrared, fine, but during daytime, certainly also it emits infrared along with its other kind of radiation. Means this is certainly not true by the nature of the Planck's law, because how does the ground know when the sun sets anyway? How either during daytime or nighttime, the Earth will never aware of it. Whether rise of sun or setting of the sun, Earth doesn't have. Means whenever it is maintained at any temperature, certainly it has to emit the radiation. Okay, means for now, let us dismiss, let us not accept the conditions or statement in such a way that it is not true. They can call it as a hogwash. The surface of the earth emits radiation all the time, including early mornings, midnight, even cool time like winter, at all wavelengths. But surprisingly, it is true to regret. One of the picture what we are expecting to see the emission of the wavelength. This electromagnetic radiation is similar to that of waves, they can call. Electromagnetic waves are simply the oceanic waves. There is a similarity comparison they can call. If you are a surfer, means those who are moving in a boat actually for surfing, probably check the swell of the forecast, swelling in the sense enlargement of the forecast for wave height, that depends on the wave height, and also periodicity to head out of the water, means to move out of the water. Means the best wave for surfing for a long period, which helps for separately and clearly define the individual waves to a great extent. But wave periods may go for about some 12 to 40 seconds as an ideal, depending on the height and depending on the nature, how long it will take to reach. Actually, surfers will decide to move or not of that kind. It is only a comparison, nothing to do with our laws. With this, we'll come to a law called the Wien's law. Sometimes they will call it as an Wien's displacement law to a great extent. On the right side, you are seeing a graph or pictorial representation of bars starting from the darker color to a lighter color at the top. Maybe it looks like reddish in color at the bottom. As you go towards the top, maybe an yellow or a white to a great extent, actually, white to a great extent of that kind. What it says that the dark red color is at about 600, brown red. Above that is 650 is in brown red. Dark cherry they can call. Cherry, light red, orange of that kind around 9,930 degrees Celsius. If you come to the top, it should be about white is about 1,200 degrees Celsius. Means colors are temperature dependent, or at different temperatures, the colors will vary. What you mean to say that earlier we discussed in such a way that there is no discrimination between color and wavelength. In fact, it is not like a color, how that we perceive, how that our inception goes actually. Each and every individual wavelength leads to some kind of a color. Some kind of a color need not be restricted with only the 7 colors what you are observing from the dispersion of a color through a prism. All matter emits radiation at all wavelengths. It does not depend so equally. This is where this law comes, that is Wien's displacement law. What it states that it states in such a way, wavelength of the peak emission is inversely proportional to the temperature of the emitting object. Peak emission means objects emit shorter wavelength and with the maximum emission. The cooler objects emit the longer wavelength. Certainly, might have observed the law in action all time without even realizing it. And to know more, let us take one example here, not be what I shown here. My God, it is a hot rod. Don't try to touch. Of course, not now here. If it is hot in principle, actually, hot steel bar. Which end might be you pick up to pick up the rod? Can you hold here on the right side? Actually, certainly not. Okay, if the rod is like that, you want to shift it from one place to another place. Actually, you can't shift it. Actually, what happens? The right end, it looks very hot. But why does it look hot actually? Why not on the left side? Looks like a whip gaya, if we expect actually, this is the white and reddish in color. This looks with the bluish. All the wavelength peak emission for the right side of the bar is obviously shorter than what left side of the peak emission. Means it is shorter. Okay, you see here in such a way, the shift in the peak wavelength as the color changes from red to the orange and then to yellow as the metal's temperature increases. As metal temperature increases, the peak emission emissivity will also increase. That changes in its color. What I want to say is in this previous slide is that we should not, or I should not, point out what that even thought the steel bar is a yellow-white color at the end, or the peak emission is still in the infrared part of the electromagnetic spectrum. Means between the two, one has to decide that which one it should be of that kind. Peak is so close to the visible part of the spectrum, That's why there is a significant amount of visible light which is also emitted from the steel. If you judge like this, look at that photograph. Here. The steel has a temperature of roughly about 1500 degree Kelvin, okay, resulting in a maximum emission wavelength at about 2 micron, maybe particularly between 0.4 to 0.7 microns of that kind. Being this, what Planck has made is that Planck's function tells us about that the amount of radiation which is emitted or amount of the wavelength which is emitted over which it is emitted for a given temperature of the black body. Now we are coming with a concept called the black body. Okay, black bodies are the one where they can absorb all kind of radiation which is falling on it until they reach its saturation. Then they will overcome. Okay, means to say here Planck's function tells us about the amount of the emitted radiation and the wavelength over which it is emitted for a given temperature. But another law, which is similar to that of that one, inactive Planck's, also states that or is used to determine the maximum wavelength which is emitted by a black body. Which is that law? That is the Wien's displacement law. They can call Wien's displacement law states that the shorter the wavelength which is emitted, the hotter or the more kinetic energy of the object should be there. Means it means displacement law, you can expect it is a reciprocal or the maximum wavelength one can identify that in terms of the 2897 over T. T should be in absolute degree Kelvin. This wavelength should be in terms of the micrometer. If you take a spectrum, what I shown two graphs, two pictorial representation of the sun actually earlier, our sun is a yellow dwarf star with a temperature of about 5800 degree Kelvin. What is the maximum wavelength of the light that is emitted by the sun if we expect? Where does that radiation fall in the electromagnetic spectrum? Certainly it should be in the visible, there is no doubt. Wien's law gives us the clarity for that. And it also relates with the temperature. No need. We never used to go there. We never went to the sun and measured the temperature of a sun actually. We measured from the earth actually, or maybe top of the earth's atmosphere, the wavelength of the radiation which is received from the sun, and indirectly we estimated what must be the possibility of the temperature of the sun if it is at a greater distance of 150 million kilometer. How 150 millimeter? That will think it off. This is the maximum wavelength of the radiation emitted by an object. Use the above expression here. You will get about 0.5 millimeter. That is in the visible region or visible domain of that kind. Somebody is active. Okay. If you see these spectrums, sorry, I put a little large number. Okay, there are 6 panels. One is the black body emission. At the left, you can see that where the temperature is about 1500 to 3000 degree Kelvin. And in the visible portion, see that peak somewhere here. You may not be able to notice it at least, but with the position you can identify. This is the spectrum how you are getting. The second one is about some 3000 to 6500. See that peak has shifted towards the left of the graph still. Okay, between 6000 to 10,000 degree Kelvin on the right, still it has shifted left, still for 26,000 degree Kelvin left till 26,000 Kelvin. And see the right pictures how that spectrum is distributed. Same WebGuire spectrum actually, with increasing in the temperature, peak shifts towards what actually? See that here somewhere here you can expect. Okay, that is this here red color. See that emissivity goes up. Visible portion of the black body emission is shifting here actually, still that of that kind. These type of the spectral signatures one can expect from the one can expect from the thing. This is another thing. Now if you take the very broad spectrum of the WebGuire actually, they see that this visible region is at 1200 degree Kelvin, 12,000 degree Kelvin, and this is at the bottom 3000 degree Kelvin. Yeah, if you expect actually wavelength somewhere here it comes. The peak is on the right side, red in color. You can see that here it is in the blue in color. Blue peak is at blue color for the ultraviolet. This is for the infrared actually. For lower temperatures, the peak shifts towards the red part, and for higher energy, it shifts towards the blue part of that kind. still if you go, is an idealized spectrum actually, there's no doubt, of the Earth's emission, particularly red in color, okay, of the electromagnetic radiation, which is compared with the emission of the radiation by the sun, orange in color, you can see that. This is orange up to this extent actually, okay. Then after that at 300 Kelvin, 300 degree Kelvin, they can call about the temperature, mean temperature or global temperature of the Earth, 6000 degree Kelvin for the sun. And you also see that the radiated temperature of the sun is 6000, whereas that of the Earth is 300 Kelvin. But in terms of the intensity, the radiation emitted by the sun is quite large. How much large? One has to see that actually. You can see the power here on the left axis, that is 10 to the power of 13, 14 of that kind. Here 10 to the power of 7.3, 10 to the power of 7.6, 10 to the power of 7.8, 10 to the power of 7.9 of that kind. Need not be always 7, 8 only in terms of the integers. It can also go with the fraction if you are very much interested in the exact values to a great extent. This means that it gives us that high radiating temperature here, the sun's peak emission at about 0.5 micron or micrometer on short wave of the visible spectrum. But meanwhile, Earth emits at the peak emission, which is located at the infrared or at a 300 degree Kelvin of the electromagnetic spectrum. Because of this, sun's peak emission is located around 0.5 micron. We see it is having a low quality. That is why 0.5 micron is relatively low. You can see that somewhere here it picks up. But this is not the case for all kind of stars. This is valid only for a star like sun actually. Sometimes stars in our galaxy are also cooler to 600 degree Kelvin, 6000 degree Kelvin. They emit a different temperature. Their wavelengths are different and exhibit a reddish color, while others are much hotter and appears blue. Okay, if you see the picture of galaxy of galaxies, if you see the galaxy of stars in a galaxy, certainly the temperature differs. That leads with the thickness. See that they are almost 1600 degree magnitude. Can use some expressions estimating the flux emitted by the sun and the flux emitted by the Earth. If you take a ratio, okay, certainly you have a magnitude that how much the radiation emitted by sun is quite high or large. It comes with the Stephen's law, with the fourth power. The description is shown here that after observing the graphs of those two, one particular attention, you can see that the energy values on the left axis of the sun is on different units, 10 to the power 13, these are 10 to the power 7, they are not comparable. But you can calculate the numbers using the Stephen's-Boltzmann law of T to the power 4. Here, SB law states, don't go with the Sharbari Bhattacharya, this is with the Stephen's-Boltzmann law, states that the total number of amount of the energy per unit area which is emitted by an object is directly proportional to the fourth power of its absolute temperature. Should be in degree Kelvin only, not in terms of the degree Celsius. The law is in such a way. This relationship exists for satellites of remote sensing to a great extent in identifying the products on the Earth and also in analyzing the spectral distribution of the universe. It's also particularly useful when we want to understand how much energy of the Earth surface emits in the form of an infrared radiation. This relation, what you are expecting, if flux is directly proportional to the sigma T to the power 4, sigma is a constant known as the Stephen's-Boltzmann constant. Shows that the amount of the radiation emitted depends heavily on temperature, such that even small fluctuations in temperature results in the large change in its emittance, because the law says that the emissivity is of the order of the fourth power to the temperature. Small in the sense, not one, magnitude wise 4 times, it should be not 4 times, right? It is of the power of the 4. Power of the 4, it should be more actually. Then small change in temperature leads to the huge change in its emissivity. Even temperature over the sun changes by small within a percent. The flux emitted is quite high, and that flux which is reaching the planets, different planets, particularly Earth, will also change the temperature of the Earth and its atmosphere to a great extent. See that this is the surface temperature of the Earth and the sun, they are compared together. See that this is at 6000 degree Kelvin, preferably about 5700 degree Celsius, they can say, minus 273 you can take. This is at about 288, average temperature of about 15 degrees Celsius. What it says that, using Stephen's-Boltzmann law, let's compare these two images with the sun's average surface temperature and the Earth's average temperature. What it says that there is a consistent with the Stephens-Boltzmann law that the sun emits more radiation than the earth. No doubt out of it. Okay, you also agree. But thing is that you don't have a law, you don't have an explanation for giving the significance, for giving the for validating your comment in such a way that where the radiation emitted by the sun is quite large compared to the radiation emitted by the earth. Take the temperature of those two, then estimate the flux. By estimating the flux, you'll come to know that how much it should be more. Roughly, it is about 1,60,000 should be more than that of that kind. Take the power sigma t to the power of 4, sigma gets cancelled for the flux, t by t for the sun to the t for the earth. If we expect t for the sun is 6,000, t for the earth is about roughly 300. If you make actually 6,000 by 300 makes 20, 20 to the power of the 4 gives you the value of the order of about 1,600 times. So sorry, 1,60,000 times more than that of the radiation which is emitted by the earth. Big days. These are the same things. If the flux is different, certainly Wien's law explains that why the wavelength of the radiation emitted by the sun and the earth is different. This is at a hotter temperature, that is why it emits in shorter wavelength. See that shorter wavelength of that kind. This is relatively cooler, it emits in the longer wavelength. The terminology has come from these two definitions such a way that the sun is maintained at a higher temperature of about 6,000 degree Kelvin with the shorter wavelength. The earth is at a distance at a temperature of about 300 degree Kelvin actually at a longer wavelength of that kind. Means to say that object have to transfer or energy has to transfer from hotter to the cooler regions. Hotter to the warmer to the cooler regions, energy has to migrate. Okay. Being a metal, the transport of the energy is through conduction, no doubt. If it is a fluid, it is convection. If not, if it is a space without the media, should be in terms of the radiation. How it will do? Just I'm explaining with one example in such a way that from daytime, for example, if you take hot air rises up, cool air sinks. Means during daytime, for example, this is the daytime what you expect actually, daytime, hot air rises and moves towards the cooler region of the ocean and sinks, it makes the circle or cycle of that kind. During daytime, hot air from the land moves up and makes the circulation. During night, this breeze is can called the sea breeze. Means from the sea, you can expect the breeze towards the landmass. During night time, what happens actually? Cool air moves towards the ocean and hot air comes to the land. There will be circulation. Great, thanks to the nature in such a way that it makes the perfect balance. How it has to happen? Always there should be a transport of the energy from hotter to the cooler region of that kind. See these two bottom panel in such a way. Latent heat which is released when the solid ice absorbs the energy, it gets melts and converted to the liquid water. Liquid water, after absorbing the energy, gets evaporated, becomes the gaseous phase. But what happens? This is the formation of the clouds from the oceanic water or any water body on the earth actually after absorbing sufficient amount of the energy and also consistent in the conditions they can call. Then during condensation, it releases energy to the liquid water. Again, it releases energy when it becomes freezes or becomes converted to the ice. This cycle is continuous. This is how that energy transported from oceanic environment to the land or land to a polar region to the land and making the earth to be a habitable planet with the good temperature. Kirchhoff's law here says that it is an ideal amount of the radiation that can be emitted by an object. In fact, it is a theoretical limit called the black body radiation. The actual radiation emitted by an object can be much small or lesser compared to what it emits with the particular wavelength. Kirchhoff's law describes the link between an object's ability in terms of its temperature to a particular object's ability to emit the radiation at a particular wavelength. It is known as the absolute body. Ability to absorb the radiation also at the same wavelength. In a simpler way, an object whose temperature is not changing, or if the temperature remains constant, that object absorbs the radiation well at particular wavelength, will also emit the radiation in the same wavelength. Means one implication from the Kirchhoff's law is that if you want to measure a particular constituent in the atmosphere, for example, like a water vapor, we need to choose a wavelength that is emitted well by the water vapor. Otherwise, we can't detect it. But unfortunately, water will not emit the wavelength, single wavelength. It is having the multispectra. Need not be a continuous spectra, but also discreteness. That one has to see that. For example, if it is a composition like an uranium, it is having a particular wavelength. If it is a radium, particular wavelength. If it is an iron, it emits in particular wavelength, maybe 1 or 2, doesn't matter. Okay, with the composition. But for example, oxygen, like atomic oxygen or molecular oxygen or triatomic molecule of oxygen, like an ozone, different peaks are observed. Water vapor in a different mixture will have a different wavelength. However, since water vapor readily emits at our chosen wavelengths, it also readily absorbs the radiation at this wavelength, which is going to cause some problem in the measurements. What kind of a problem? One has to see that. Being this, how do we measure the intensity of the radiation which is emitted by an object, which is as a function of the wavelength or for a fixed temperature? You can see that being a research problem, we can take that radiation carries away energy and therefore cools the object because it carries from hotter to the cooler region and the object becomes cooler. Some of the radiations which are coming from the object may be reflected or transmitted depending on the property of the radiation which is incident on it and also the property of the material. What solutions you can choose? Use it as a black body, and black body is a body that absorbs the radiation at all the wavelengths which is fallen onto it. It does not reflect. Black body does not reflect, but it emits the radiation back, or it sends the energy back. It reaches the thermal equilibrium with the temperature, and the emissivity must be equal to 1. Emissivity is the measure of the fraction of the radiation or the energy that is absorbed by a body, absorbed by the black body. See, this is one kind where it can link. That law is known as the radiation law. See that as the temperature goes up, the peak also goes up. As the temperature goes up, peak shifts towards the shorter wavelength. No much description. You can read that better actually. Wien's law and Stephen's laws are well connected. Wien's law is expressed in terms of the same case, what I told. Stephen's law, which is the T to the power 4, means Wien's law explains the shift in the peak. Why peak shifts towards the lower side of the wavelength or the higher frequency? Because temperature increases. But the growth in the curve, area-wise, if you take 4000 degree Kelvin, 5000 degree Kelvin, 6000 degree Kelvin, increasing in the area or growth of the area is explained by the Stephen. Means this growth is very abrupt since it varies as the fourth power of the temperature. That is the problem. In this sense, that is the crux actually. Because why abrupt? Because 4000 to 5000 it is not linear actually. Because temperature follows fourth power of the order and peak also increases to a great extent. This is another one. Planck's curves are used to show the amount of the energy which is emitted. As the black body becomes the hotter, it emits the shorter wavelengths and also greater intensities. Being this, see, you'll get then one more law called the Rayleigh-Jeans law. Rayleigh-Jeans law agrees with the experimental results to the lower frequencies or for shorter wavelengths, shorter wavelengths, but strongly it disagrees. See that these are the three laws. One is the Rayleigh-Jeans law, it's going up. Planck law is mentioned in blue color for the sun only. Wien's displacement law is also in some other reddish color of that kind. Both are matching well. Rayleigh-Jeans law agrees well with the wavelengths for the lower frequencies here. Okay, it disagrees with the higher wavelengths. Rayleigh-Jeans law is an approximation to the spectral radiation of the electromagnetic radiation for the function with a black body, which is maintained at a given temperature. This is up to this extent you can keep. If there are any queries, I can respond to you right now, or Professor Ira sir will engage the class for you. He instructed me for today. These four laws you remember: Rayleigh-Jeans law, Wien's law, and Planck's law, along with the rest of the laws actually. But they are the good in that. But they can be used as a great tool in estimating the position and also the properties of different celestial bodies in the space. Because different elements in your laboratory and different composition also in your laboratory through several spectrums, preferably in electromagnetic, in the visible part of the spectrum of that kind. Thank you. I will end my class today. We will take next class at our convenient time during next week. There are particular questions you can ask me right now, or you can chat also. Thank you. Thank you. I'll stop sharing the screen.
Thank you, sir.
Wish you happy Deepavali well in advance.
Thank you, sir.
Thank you,
Thank you, sir. Wish you the same, sir.
Thank you.
Thank you, sir. Wish you the same.
Thank you. Thank you very much. Shall I end the meeting?
Yes, sir.
Okay, sir.
Good. Great voice.